Okay, so just a reminder, the algebra stuff that we did yesterday, that is due on Friday. It's going to be about a week, probably mid-week next week to late next week, in which we start using that algebra directly in some of our questions. So if that homework assignment is providing you issues, and you're not getting it done, or feeling comfortable getting it done, make sure that you're taking the initiative to find out what you need to be doing to fix that, okay? Because I do not want you to be hamstringed when we start talking about these types of questions for geometry, and when you have to come up with equations of lines and analyze slopes and that kind of stuff, develop relationships and understanding of what is going on in the geometry part, because your algebra skills are lacking. So you got a week now to get that stuff kind of squared away. Nobody in this class does not have the ability to write equations and lines and stuff and that kind of stuff. You all have the intellect to be able to do that. It's whether you want to or not is another story. Okay? Yes?
I mean, did you say something about extending the thing?
Yeah, just do Friday.
Okay.
Do Friday, 11:59 p.m. Yes. Don't worry about it first. I would like you to watch. If you don't understand what's going on, watch the video. But I have to go back in and get that point that everybody wants from that question. I got to go back and give that to you. So what this chapter is about, is that we're going to start drawing segments inside triangles. And there's going to be special kind of requirements that need to be made to develop these segments. And then we're going to analyze what the relationships are between those segments and between the segments in the triangle. Okay? This is what I find out in the past is that there's a lot of stuff in this chapter that is completely new to you. Okay? There's some terminology in this chapter that is going to be problematic. It's going to be hard to keep straight. Okay? Because there's so many different segments that we deal with. And then because we have 3, 4, 5 different segments that we deal with, and each one of those has maybe 1 or 2 different properties that associate with them, it gets messy if we can't keep things straight. Okay? So I'm just kind of giving you that forewarning now. This chapter is not the easiest of the chapters that we go through. Okay? Yes? We will have a test before break. Okay? So, 5-1, the first thing we talk about is mid-segments of a triangle. Mid-segments of a triangle. That's the title of this section. And I want to ask you this question. If I look at that triangle ABC, okay, or, any triangle, ABC, so we're going to move these around, but I want you to tell me what you know about those blue points.
The midpoint?
They are midpoints. Those blue points, D, E, and F, are midpoints of their respective sides, or the sides that they are on. Okay. So, now, if I take any 2 of those midpoints and connect them, that blue segment is referred to as a mid-segment. Okay? That blue segment is a mid-segment. Now, the idea was I said I could take any 2 of those points. Then I could take D and F. That red segment is a mid-segment. Does that make sense? Okay? And I could take E and F, and that purple segment is a mid-segment. So how many mid-segments does a triangle have? 3. Okay? Now, it's not uncommon, but a lot of times we don't deal with all 3 at once. Okay? So, in building the relationships that we're interested in today, we're just going to look at one of those. So maybe I should look at D to E. Okay? But that is a mid-segment, and there's going to be some relationships that are presented inside a theorem that we're going to try to investigate a little bit today. That's the definition right there of a mid-segment. Now, it's a mid-segment of a triangle. And the way I write that, hopefully it sheds light on the fact that there are other shapes that have mid-segments. So it's good to know it's a mid-segment of a triangle, okay? Because a mid-segment of a trapezoid is a little bit different, okay? So the segment connecting the midpoints of 2 sides of the triangle, okay? Does not matter which 2 midpoints you're using, okay? You always generate a mid-segment. All right. What? What? Yes, I'm going to the workout tonight. All right, so going back to this picture here. I have now filled in the distances of those two segments, DE and AC. So what I'm interested in here is the mid-segment and then the segment of the triangle, or the side of the triangle that the mid-segment does not touch. Okay? So those two, AC and DE. What is the relay? Look at the numbers there. Okay? And right here I've got the algebra happening. Kind of hard to see that division sign there. I'm taking DE divided by AC, and look at what happens. As I change those quantities, what is my quotient? It's always a half, right? Even though the numerator and denominator change, the quotient still maintains as 1/2. So what that tells you is that that blue segment is always half the third side. Does that make sense? Okay, half the third side. What is another relationship that you think is probably true about that blue segment in the third side? Let's go off of looks here. It's parallel. Okay, so those blue segments, okay, if I look at the slope, that one's 0.24, that one 0.24. Okay, no matter where I move them, now the slopes change, but in comparison to one another, are they still the same? Okay, so those two lines are parallel. Those two lines are parallel. Okay, so those are the two features that we need to understand, or that we need to know for a mid-segment. Now, that's true for that mid-segment. If I do the same thing, let me just delete that one, and now let's put in D to F, and look at that one, okay? I'm not going to put the slopes in, but would you agree that those slopes are going to be the same? All right, and if I look at the distances then, distance of that one, 8.48, distance of that one, oh, not giving me the perimeter. I don't know if I'm going to be able to find the distance real easy maybe that way. Okay. I'll take 8.48 and double it. Do I get 16.96? Yeah, okay. So every mid-segment is going to have that relationship that is parallel to one of the sides of the triangle, obviously the side that doesn't touch, and it's going to be half the length of that side that it does not touch. Okay? So I'll give you a minute to write that down. That's the theorem. I'm having people come to me and ask me questions about, I'm doing okay on homework. When we do questions in class, I can follow along and understand, I can be directed and shown how to do something, and then that problem I can do it again on my own. But then when I get something new on homework that is similar but not the same picture, or on a test or quiz when it's similar but not the same picture, I don't know where to start. I don't know what to do. And then I go back through their tests and I look at the questions that they're missing, and they're missing a lot of vocabulary. Okay? If you're missing a lot of vocabulary, it tells me that you're not going to be able to address and utilize the theorems in the correct way, because the theorems use the vocabulary, right? If I don't know what alternate interior angles are, I can't identify them and find them. When the theorem that says alternate interior angles are congruent, that means nothing to me, because I can't tell you which angles then are congruent. Okay? I can't set up a relationship. If I'm setting up the incorrect relationships because I don't know the theorems, because I, in respect, don't know the vocabulary that's being used in them, it doesn't matter how good I am at algebra. I can be the best. I can be, Stephen Hawking good at algebra. But if I can't set up a single correct equation through the use of definitions and theorems, it doesn't matter. My algebra is useless. Does that make sense? Okay. So keep that kind of thing in mind as you are preparing for tests and quizzes. Go back and look at your tests and quizzes. If we're not doing well, see what types of questions you're not doing well. Or is it always vocabulary that you hate for this class? You struggle with this class. You hate it because you're not good at it. Then you have to attack that. You have to address that somehow. Make flashcards, okay? Quiz looks good, but it's not great. Quiz looks good because it's convenient. But when I type something out, it's not as impactful as when I write something out. 6 times more impactful to write something out than it is to hear something, okay? Typing is more impactful than hearing, but writing is more impactful. It's going to stay with you longer. It's going to have more meaning to it, okay? At the same time, if I have index cards and I'm writing out definitions and theorems on them, I can draw pictures so that when I see a definition, I can also see the picture at the same time. And now within my problems, if I can see that little picture occurrence in my problems, maybe it starts the ball rolling and jogging my memory and says, okay, this picture elicits the thought of this definition. This definition, what did that tell me? Okay, it's this idea, it's this concept, it's this object. And now how does that relate with the theorems? What do the theorems say about those objects? Okay, that's the way that I think we should be preparing for testing quizzes. Okay, being comfortable with our vocabulary, that's going to allow you a better comfort level with your theorems, and then being able to use them and apply them inside the algebra problem. So when you see the theorem that a midsegment is parallel to the third side of a triangle and is half as long as the third side of the triangle, that means nothing to me if I don't know what a midsegment is. Okay. And like I said, I'm seeing some of that on tests and quizzes from people that are struggling, doing well on those, but feel like they do okay on homework. Okay, that's just my 2 cents, my suggestion to you. I want to prove this. Okay, now the proofs that we've been doing, okay, they're not. Of the types of proofs that we can do in mathematics, I think two-column proofs are like the most boring. Okay. I think a lot of people appreciate eventually the type of proof that we're going to do here in a moment. It's called a geometric or analytical geometry proof, okay? Which means that basically we're going to take a coordinate plane and we're going to work inside the coordinate plane and we're going to use formulas to help us realize a true statement, realize this idea of parallelism or this idea of distance being 1/2 the third side. Now in doing this, we remember what proofs do. Proofs, the reason we do them the way we do them is so that we eliminate any counterexamples that could be possible, okay? So we don't like to use specifics, right? We don't like to use specific numbers inside our geometric proofs. So inside a coordinate proof, the same thing occurs. I don't want to say that my vertices of A, B, and C are specific numbers, okay? We're going to use arbitrary numbers, meaning they can be just random, be anything they want to be. Okay, so we'll kind of talk about that as we start setting this up. But this is going to be a little bit different of a proof than what we've seen in the past, and I think it's a little bit more enjoyable, and the conclusions that kind of fall out are a little bit more like the aha moment. I see what's going on here. I see the understanding of the reason why we did what we did. So here's how I want to start this. Let's say I have this triangle, okay? And this triangle is just a random triangle, meaning that it could be any triangle that you want, okay? When I provide this, now I'm going to say I'm going to provide this in front of you, and it's just like maybe a cardboard or plastic cutout, and you set it on your desk, okay? Can you rotate that and still have the same triangle? Can you flip it and move it around, translate it left, right, up, down, and still have the same triangle? Okay, so here's the idea, okay? I give you a bit of transparency. You guys know what I mean by transparency? A clear piece of plastic, okay? And I, on that transparency, draw an X and Y axis, okay? And if I wanted to, maybe a grid. Is that all right? Would you guys agree that if you had that free-floating triangle in your transparency, that you could always take that triangle and put point A, and really any point that you wanted to, so that it matches up to 0, 0 on your transparency? Does that make sense? Both those things, the transparency and the triangle, are floatable. They move around, so you can do that. Okay? At the same time, I should be able to rotate this triangle, put my hands on that triangle, and think about sliding, rotating it down, keeping A where it's at. Can I rotate this thing down so this line here becomes my x-axis? Does that make sense, everybody? So it's kind of a little bit harder for me to do this, but I would rotate that down, and then maybe this B point would have came to about right there, maybe. Is that all right with everybody? So no matter what triangle you have, you can always take it and move it so that a vertex is located at 0, 0, and another vertex is somewhere on your x-axis. Okay? Now, here's where we start to do things that are going to allow us to prove this to be true for every single triangle, for every single situation. I do not care about the numbers on either axis. Okay? I don't even care about F either. Okay? I'm just looking at one mid-segment. Okay? And I'm going to zoom out a little bit and do that. Okay? So we should be able to take every triangle and do that with our axes, right? Okay? Now, here's where it gets a little bit fuzzy for some people. Okay, but this is what we refer to as the analytical part of this. We call it analytical geometry. Okay? We are going to provide coordinates for points A, B, and C, but they're not going to be numerical. They're going to be variable. Does that make sense? Meaning they could be random, anything they want to be. However, what do you know the ordered pair for A has to be? 0, 0. Okay? So we make A 0, 0. Okay? And that's always kind of a nice thing to have a lot of times in all these types of geometric proofs that we do. When you get to college algebra, algebra 2, that kind of stuff, you will do more of this for other formulas that you, and other relationships that you see. When we talk about my college algebra students are, in about a week or so, we're going to start doing this stuff with circles and ellipses and hyperbolas, okay, called conic sections. And the formulas that are generated from or for those things all come from this kind of practice, this process, okay? So that's 0, 0. Now, when I come to C, I want to label C as an ordered pair. Okay, careful. Which coordinate has to be 0? Well, that means then if the x-coordinate is 0, then to go from the origin, I don't move anywhere left or right, correct? So doesn't the y-coordinate here have to be 0? That makes sense to everybody? Okay, so the y-coordinate of point C has to be, because it's on the x-axis, right? Everything on the x-axis has a y-coordinate of 0. Now, you said 10, right? Okay, so if you want that to be 10, that's fine. But somebody that let it be 12 would have the same conclusion. Somebody that let it be 215 would have the same conclusion, right? So to take care of all those situations where it could be 10, it could be 12, it could be pi, it could be 215, it could be radical 4, or radical 40. Radical 4 something is 2, right? So to take care of all those potential values that could go there, we wrap that up with just A and say that A is just a real number. It could be anything. It could be 10, it could be 12, it could be radical 40, it could be pi, it could be E. It doesn't matter. Okay? It is some real number. Is that all right, everybody? All right. Now I'm going to move B around to see if you guys can make an argument for what we have to allow B's ordered pair to be. If I put B right there, do you know what the x-coordinate of B would have to be? It'd have to be 0. Why? Okay, because on the y-axis, it is on the same vertical line that A is on, right? Okay, so if it's on the same vertical line that A is on, it has to have the same x-coordinate. They're stacked on top of each other, right? Okay. What if I put B right there? What would the x-coordinate of B be? It'd have to be A, right? Because it's on the same vertical line that point C is on, so they have to have the same x-coordinate. And the x-coordinate for C is A, so B would have the x-coordinate of A. Now, because of that idea, think about what we would have to have for my x-coordinate if B is right there. Can it be something that I've already defined? Can it be 0? No. Can it be A? No, because we just showed the two spots that they would be if it was 0 or A, right? So it has to be something new, correct? Okay, so I'm gonna put lowercase b. Okay. Now the y-coordinate. Is the y-coordinate going to be the same as any other y-coordinate that's up there? No, it's because the other y-coordinates are 0, right? Obviously, point B does not have a y-coordinate of 0. It's something different. Where do we let it be then? Probably C. Okay. Now you can hear some people saying other things. Okay. Let it be D or R or square or something like that. You could let it be any symbol you want to. It doesn't matter. Okay. We just predominantly use A, B, C, D, E until we run out. Okay? All right, so is everybody comfortable with that? Think about what this does. If A, B, and C are arbitrary values, meaning they could be anything, that generates every single triangle that we could ever come up with of any size. Is that right? Okay. So as you start adjusting those values of A, B, and C, it will generate every single triangle feasible. Okay. So if that's the case, let's find the midpoint. Let's find D. What is its order pair? Okay. Now it's a little harder because remember finding the midpoint. Does anybody remember the midpoint formula? Guys, remember seeing this from before? We used this in chapter 1. We used a little bit in chapter 2 and 3. Okay. So that thing is going to repeat itself. It's going to keep coming back every once in a while. Okay. I want to find the midpoint of AB. Okay. Which is point D, right? I want to find its ordered pair. Okay. Now you guys know how to do this if B was like 10 and C was like 12, right? You take 0 plus 10 divided by 2, and then take 0 plus 12 divided by 2, right? But if the BC was like 13 and 7, okay, you would take 0 plus 13 divided by 2, 0 plus 7 divided by 2, right? Well, now let's use these arbitrary values. If I'm adding my x's together, x1 and x2, there's x1, there's x2. What's 0 plus b? B, and then divide that by 2. This is a b over 2. Now I want to do the same thing for my y coordinates. Add y sub 1 and y sub 2 together. So it's c plus 0, c, and then we'll divide by 2. So what that will do for me is that will always give me the location or the coordinates of D when I specify what I want lowercase b and lowercase c to be. Does that make sense? It's kind of a shortcut way of getting that ordered pair without having to go directly through the midpoint formula. Yes? Say again? Yes, yes. So this is the reason why we chose that point to be 0, 0. We could logistically, logically put this point anywhere we wanted to. So it could be a 1, 1, it could be 1, 2, it could be 1, 3, whatever. But then finding these things, these would be more difficult looking formulas. But so if this point was 1, 0, then yes, it'd be b plus 1 divided by 2. Does that make sense? But it allows the algebra to be so much simpler if we let that point A be 0, 0.
So would the midpoint formula basically be finding the average of the line?
Yes, yes, yes. And that's you've heard me say that when we take when we first introduced the midpoint, we said the average of the x's divided by the average of the x's comma the average of the y. So yes, that would be true. All right, so now we want to do the same thing to find the ordered pair for E. It's a little bit more tricky because we don't have a 0, 0 point. So I'm going to add my x's. So one of those coordinates is going to be A, and the other one is B, right? Add those together, you get A plus B. You're going to divide that by 2. Now I'm going to do the same thing with my y's. 0 plus C gives me C, and I'll divide by 2. Okay? So now you have, no matter where A, B, and C go, wherever those points go, those capital letters A, B, and C, wherever they go, you now have formulas that will give you the midpoints for the segments A, B, and CB. Is that right? Which ultimately give you the endpoint of your mid-segment. So I'm going to draw on my mid-segment. Okay? And I'm going to actually clean up some stuff here in my picture, just so it's cleaner for you guys to see when we're working through this. I no longer need point B. Point B has served its purpose. My midpoint formula has served its purpose. I just need that stuff left over there. one of our theorem, or one of our facts in our theorem said that the mid-segment, so DE, was parallel to AC, right? Okay. If I'm trying to prove that, what is the algebra that we use to prove segments parallel? Rise over run. We got to check out the slope of these things, right? All right, so let's do this. Let's find the slope. The slope of any line, let's write the formula up here, is y2 minus y1 over x2 minus x1, right? Is this a x1, y1? Could this be an x2, y2? All right, so let's find the slope of AC. Slope of AC, y2 minus y1 over x2 minus x1. What's 0 minus 0? 0. What's a minus 0? A. Now remember, a is just a number, right? What's 0 divided by any number other than 0? A cannot be 0. And just answer this question first. What is 0 divided by any number? 0. Unless that number was 0 itself, right? Because 0 divided by 0 is an indeterminate value. It's undefined still. Okay? But hopefully we understand that this line that A cannot be 0. Because if that value was 0, wouldn't that make point C on top of point A? Does that make sense, everybody? Okay? So we do get a slope of 0 here. Okay? That's what I'm trying to prove. Yeah, that was it's the first condition in that theorem that says if you have a mid-segment, then it is parallel to the third side and in half the third side. So I'm trying to figure out whether we can prove that parallel idea. Okay. So I've got the slope of AC. Let's find the slope of DE.
Wait, what is that? Is that the math up there? Wait, what is the N?
Slope, and then of AC, segment AC. So this would be slope of segment DE. Okay, so now, would we agree that when we find the slope of DE, that could be x2, y2, and this could be x1, y1? All right, so let's take our y2s, or our y2, which is c over 2, minus our y1, which is c over 2. It's a nice thing right there. And then take my x2, a plus b over 2, minus my x1, which is b over 2. Now the algebra up top is pretty easy. What's c2? C over 2 minus c over 2? 0. Now I just got to make sure, because a lot of times when you get the numerator to be 0, you can say, well, 0 divided by anything is going to be 0, right? So I can maybe make the jump or the conclusion that this is 0. I just want to make sure that my bottom doesn't become 0 itself, because then that would be an issue. Does that make sense? They can't have 0 divided by 0, even if the numbers are the same. Okay? A lot of people say, 2 over 2 is 1, right? So they say 0 over 0 is 1. It's not. It's still undefined. Still cannot divide by 0. Common denominator here, right? So if that's a common denominator, can I just do this and go a plus b minus b all over 2? Okay. So what's a plus b minus b? A. So just get a over 2. Well, what's 0 divided by a over 2? If a is just some random number. That's 0. Is that okay with everybody? Okay. And again, a, we know, cannot be 0 because then that would put point C on top of a. So I get slope to be 0. Okay, now I don't really care what the numbers were, that the slopes were both 0. I care how they relate to one another. If the slope, we just see the slopes are both now the same number, right? So what did we just prove? That those two lines are parallel. Because the slopes end up being the same value, the same result, we get parallel lines. Okay? Now, I want to go and do the distance part. Okay? So, we're trying to figure out that the distance of DE is 1/2 the distance of AC. That's what we're going to try to prove here. Distance of DE is 1/2 the distance of AC. Okay? Now, this should be somewhat easy to do. Okay? If I want to find the distance of AC. Okay, look at the distance of AC. It's a horizontal line, right? It's on the x-axis. How long would that distance there be? It'd be A. Is that right with everybody? If C was located at 12, 0, the distance would be 12 units. If it was located at pi 0, the distance would be pi units. If it was located at 103, 0, the distance would be 103. Okay? Because our starting point is 0, 0, we're going out to a point A, 0, so we've traveled A units. So that part was pretty easy, right? Find the distance of one of those segments. The other distance is a little bit more rigorous, okay, because we have to use the distance formula. Remember the distance formula, x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, right? I'm going to try to find the distance of DE. Can I let E be x2, y2, and D be x1, y1? Let's just plug those things in, see what happens. I take A plus B over 2 minus B over 2. And we'll square that. Okay? I'm going to add to it the difference in the y's. So y2 is C over 2 minus y1, which is C over 2. And we'll square that. Okay? Now, once we've got that, all we have to do is evaluate. We have to rely now on our algebra skills. What's C over 2 minus C over 2? 0. What's 0 squared? 0. Do we all see it? That wipes away right there. And all you're left with then is this. We have A plus B over 2 minus B over 2 squared. Well, didn't we already do that math? A plus B over 2 minus B over 2, what did that equal? A over 2. So now underneath my radical, I have A over 2 squared. What happens to that power of 2 and that root? What do they do to one another? Cancel out. What are you left with then? A over 2. That's the distance of DE. How does that compare to AC? DE is half AC, right? Does that make sense, everybody? All right, and so that relationship falls out using arbitrary values, using letters that represent numbers, and we never use specific values, right? Okay, now our formulas kind of create like that, the midpoint formula creates that denominator of 2 and all that kind of stuff for us. So those were specific values. But A, B, and C were arbitrary. They could have been anything. So that means that A, B, and C, those points, depending on where I let lowercase a, lowercase b, and lowercase c be, could generate any triangle that we could ever imagine. And if I could create any triangle that I ever imagined, this information with those lowercase a, b, and c values is always going to be the same. The a over 2 and a for the length of those segments, and I always get the slopes to be the same. Okay? So that's what we call a kind of analytical or analytical geometry proof, where we're going through using algebra formulas, algebra concept according to plane, to prove geometric concepts. Okay, and we do quite a bit of that as we move on through the next couple courses. Okay, we'll come back to this again at some point later on. Your end of course exam doesn't ask you usually to prove anything like that, but it will give you a picture at some point with, you know, ordered pairs that are letters A, B, C, D, and that kind of stuff, and ask you to make judgments about distances and lengths and stuff like that. Okay, so you will have to have a little bit of understanding of this stuff for the end of course exam. So we're going to continue to practice this and work with this with other theorems as we see them. Okay. The last thing I want to talk about is maybe one or two more examples of using the mid-segment theorem. Okay, using the mid-segment theorem is not hard. If you can all divide by 2 or multiply by 2, you're going to get the right answers. Okay, but I want you to see where this stuff is used and why it's useful. Okay, you guys know what direct measurement means?
Directly measure something?
Direct measurement. If I'm going to directly measure something,
Would that be like getting a roller or something?
Yep. If I want to directly measure the height of my whiteboard, I get my tape measure, I go up to it, and I directly measure it. Does that make sense? I touch it. Okay? 3 feet. Okay? So I touch it. Okay? I can address it physically. Okay? Indirect measurement, let's say that I want to measure the height of the ceiling. Okay? Up there. I can't do that though. Okay? But maybe, let's not use the ceiling. Let's do it this way. Let's say that you guys saw this last year. If I want to measure the height of like a pine tree, okay? Pine tree is maybe like 40 feet high. So I can't get on a ladder and get somebody else at the top and hold my tape measure, all that kind of stuff. But could I wait to a particular time of the day where that pine tree has a shadow? Can I measure that pine tree shadow on the ground? That's safer to do, right? At the same time, can I measure my shadow on the ground? Okay. Do I know the height of myself? Yes. So I could use proportions to find the height of that tree. You did this last year. You use proportions to find the height of that tree without having to directly measure it. Does that make sense? You use other known facts and other algebra and geometry to do that. That's called indirect measurement. Okay? Direct measurement is walking up to something and physically measuring it. Indirect measurement is using other measurements to develop the length or the angle measurement that I'm really interested in. Okay? So right here in this picture, we've got some type of chasm, some type of maybe sinkhole that we don't want to cross. Okay? We don't want to get too close to it because it's just maybe dangerous. Does that make sense? Okay? Maybe if you go to Yellowstone, you see those sulfuric geysers, those basins that are you touch them, you'll dissolve yourself, right? But maybe we want to know some measurements on them. Okay, so this is how we would do this. Okay, we're going to go and we're going to put a marker up here at point B and a marker at A, and that just reminds me that's what I want to find the length between B and A. Okay, from there, from A, I'm going to walk on solid ground back to some arbitrary point E. Okay, and we'll talk about how we have to choose E here in a little bit. Right, I put a marker at E. Okay, now as I walk that distance, could I measure that distance? Yeah, it's on ground, right? I could, as I'm walking, maybe I use a tape measure, or maybe I just pace it off or whatever. But if I find that to be 200 feet, can I find the location of C? I can take half, right? So I can go half and find that midpoint, correct? I then go to B. I'm going to walk straight back to E again. So I create this triangle, right? Now that distance might be the same as AE, but it's probably likely to be different. Okay? But could I measure that distance? Yeah, let's say it's 80, so what would D be located at? Be 40 feet, right? But D would be, I could find the midpoint there, correct? What is that segment right there called? It's a mid-segment. And you know a relationship between that mid-segment and AB, right? The parallel in the mid-segment is half of AB, right? So what do I need to do to 46 to get AB? Double it. So I know then, because of my geometry, that A to B is 92, and I never had to put anybody in a boat with a tape measure to do that, right? Okay? So there's a lot of things that we are interested in finding measurement of that we can't physically get to. We know a lot about the surface of Mars, don't we? Anybody ever been there? Okay. We knew a lot about the surface of Mars before we had that rover. Okay? Because we had Hubble, right? We could take pictures of it. Okay? We can use, and we could find measurements and critical information about the surface of Mars and characteristics of Mars without ever going there. Okay? And even the rover that's there right now is still using cameras and that kind of stuff and lasers to measure distances that it doesn't necessarily travel. Does that make sense? Okay. So that kind of thing is indirect measurement, and it's very, very useful. It's very, very accurate. Okay. Does that make sense? A lot of stuff that we do in the rest of this class, guys, is going to be about indirect measurement. The calculator button, sine, cosine, and tangent, those address being able to find indirect measurement very quickly. Okay. There is an assignment 5.1 on Math Excel. I want you guys to address that. Tomorrow, I'm going to, I already covered fourth period. There's a last slide here, number 8. I'm going to start class off with that tomorrow with you. It's a quadratic formula question using the mid-segment stuff, so you'll get practice with that. That's kind of the plan. 5.1 due tomorrow. Remember that algebra review that I gave you yesterday is due on Friday. Okay, guys, I understand. I really do.